All right, so if we do CPS conversion, it turns out that tail calls are easy to implement. So here's an example where we have a tail call. So we essentially have the same structure as before. We have a square function, but instead of calling multiplication as a primitive, it actually calls it a function which does the job. So mult here is actually a function of two arguments that multiplies A and B. So this is actually a tail call. So if there's a call to square, square basically just propagates the call to multiply. So this is a tail call, and then multiply and return directly back to the call to square. So if we do CPS conversion, so we add a parameter k to mult, and to return the result, we call the function k. Square also takes a continuation k and calls multiply, and because it's a tail call, it can just pass k as an argument here. Okay? So the continuation that's created for the call to square is basically just propagated to multiply, and multiply is going to be using that exact continuation to return back from the call to square. So it's when you have a non-tail call that you have to create closures. Okay? When you have a non-tail call, you have to create a continuation, and here we're representing continuations with closures. Moreover, in the CPS converted program, there are no non-tail calls anymore. So all calls have become tail calls. And for that reason, it's much easier to implement. And once we've done CPS conversion, it's much easier to go and compile down to C. So function calls, because they're tail calls, can simply be translated to jumps. There's no context to save or anything like that. You basically just transfer control to some other location in your code. So now I want to explain how this can be done systematically. So this is sort of the details of CPS conversion. And to express the rules of CPS conversion, I introduced this notation of a box, an expression in a box that has another expression underneath. So here, this expression expresses a scheme expression that is the result of the CPS conversion of expression E in a continuation C. So C actually represents the consumer of the result of the evaluation of E. So E will have to somehow call C to transfer the result to that continuation. So notice that in the patterns, in the rules that I will be giving, both E and C are expressions. Okay? So this expression is really a source-to-source transformation. There's no real evaluation of these expressions that occurs. It's really text in, text out. Moreover, notice that because of the way CPS, the rules are sort of arranged, C will always be either a variable or a lambda expression. So there are certain constraints on the code here. E, there are no constraints. It's a scheme source. So anything that's available in scheme is available within the expression E. But there are some constraints on C. So C here is either a variable or a lambda expression. And if it's a lambda expression, it's a lambda expression that's in CPS form. So it means that everything inside of that uses tail calls. Okay, there are no non-tail calls in C. So the very first rule is the following. If you want the CPS converted program, okay, what you do is that you will be using the CPS conversion of expressions, using the program as an expression, and using this as a continuation. So you have a lambda expression here that says, well, this takes the result. R is actually the result of that's computed by the program. What is done with this result is simply calling the primitive halt. So halt stops the execution of the program. So if we ever reach this point, if we ever call this continuation, this means this is the end of the execution of the program. So in the actual implementation, it actually also prints the result that you have here, which is convenient for debugging, but is not fundamental to the CPS conversion. So this is what's called the primordial continuation. It's the very first one that you have. It's the one that the operating system gives you when the program starts up. And if you ever call this continuation, that means the program is terminated. So here are some of the simple rules of CPS conversion. If you're converting a constant, so the lowercase c here means anything that's a constant, and within the continuation big C, then all you have to do is generate a function call to big C with the constant as argument. So it's sort of the simplest case to consider. Same thing for variables. So if you're CPS converting a variable with the continuation big C, then you simply call that continuation with that variable. Now notice what I said before. Big C is either a variable or a lambda expression. So if it's a variable, it actually represents, getting the value of the variable and then calling this variable. If it's a lambda expression, it actually means that in the resulting CPS program, we have a let. So if C here is a lambda expression of one argument, then the result of the transformation is actually a let. And you'll see in an example I give later on that this actually happens very often. And we get programs that are, if you have quite a bit of nesting, you get basically a series of lets, okay? Cascade of lets that express the sequencing of all the sort of the primitive operations of the computation. Okay, if you want to convert an assignment, what you have to do is first CPS convert expression 1, which is the value that, the expression that gives the value to assign. And you give as a continuation this lambda expression that will receive in R1 the value of this expression. We'll call set of the variable with this value and simply propagates the result of the set to the continuations big C. Okay. Here, I should say, the compiler that I wrote, assignments actually return the value that is being assigned. So this actually makes sense that the value that's propagated to the continuation is actually the value of R1. If we look at a conditional, first thing to do is the CPS convert expression 1, and the result of that will be sent to this continuation. So R1 will be the result of E1. We then have in the body the continuation an if of this value, and depending on the value, we either will evaluate 3, but CPS converted with the continuation big C as a continuation. Notice that all these rules, most of these rules are recursive. So, I mean, if E1 is actually a variable, let's say variable X in your program, then here we're asking to CPS convert X, which means in this case right here. So this, in this particular case, it will be lambda R1 blah blah called with the value of X. Okay, so it's basically let R1 X, so R1 gets the value of X, and then do the rest here, which is do the assignment and call it the continuation C. Begin evaluates E1 and then evaluates E2, returning the value of E2. So we CPS convert E1, and the continuation of this is actually lambda expression that receives in R1 the result of E1, and then we'll keep going with the evaluation of E2 within the continuation C. For primitives, if we say do the sum of E1 and E2 in the continuation C, well, we CPS convert E1, results will be sent to the continuation here. Inside of this continuation, we actually evaluate E2 within this continuation here. So R2 will receive the value of E2. So R1 is the value of E1, R2 is the value of E2, and then all we have to do is add R1 and R2, sending the results to the continuation C. For lambda expression, essentially what we do is we add the parameter that represents the continuation, and the body of the lambda needs to be actually there's an error here. So we CPS convert the body E0 with the continuation K. The thing I forgot is that the continuation C actually has to receive this, so this should be C of lambda. The continuation has to receive something, in this case the closure that's created. Okay, this slide is how to CPS convert various function calls. So instead of giving you the general rule for any number of arguments, I give it as a certain number of patterns. So if you're calling a function with no arguments, so E0 here is the function that you want to call, then you CPS convert E0, the value of that function will be in R0, and basically you call R0 and you pass C as an argument. Notice that this respects the calling convention. We've added the K as a parameter to lambdas, and so the continuation here will actually be received in that parameter. And we could go on, let's say we do the two argument case. So if we have to CPS convert this, then we CPS convert E0, we receive the result in R0, then we keep going with E1, result in R1, and then E2 in R2. And then we simply call R0 with the parameters R1 and R2, and then we add the continuation here, once again to match the K parameter of the lambda.
So your functions are queried.
Because here we're calling the function, and we're using 3 arguments.
Okay, but the first one is kind of queried, in fact.
Which first one?
E0 of E1 and E2. If you query it,
E0, E1, E2?
yeah. If you query this one,
well, if you query it,
you will get it by composition with the last one, not it?
I don't see that. I mean, the function call here is passing 2 arguments.
Yes.
And if you had a queried function, you would only be passing 1 argument. So here you're passing 2 arguments, and in fact in the CPS converted code, you're passing 3 arguments because you have to have, in addition, the continuation. So there's no querying. Okay, then there are some rules for dealing with, these are actually, you could view them as optimizations. They actually are simple to do, and they improve the code quite a bit. And that's to especially handle the case where the thing you're calling, the function you're calling, is a lambda expression. So this corresponds to a let in your program. So here, for example, if you're calling this lambda expression, this corresponds to a let of P1 to E1, P2 of E2, and then E0 is in the body of the let. So this can be converted more efficiently than with the previous rules if you do it this way. You CPS convert E1, and the argument of the continuation is actually the name of the parameter that you have in your let. So here P1 will get bound to the value of E1, and here P2 will get bound to the value of E2, and once these 2 bindings are done, then we can go and evaluate E0 within the continuation K, let's see. So this is more efficient than actually adding a continuation parameter to these lambdas. So how do we deal with call CC? It's actually very simple in the sense that there's the implementation of call CC becomes very short when we're in the CPS converted form. So here's how it works. Remember that call CC takes one argument. The argument is the function, which we call lambda const or lambda, what is the other name we had? Lambda return, etc. So the f here represents this function. We've added an argument because we're in the CPS code. So k here actually represents the continuation that call CC is receiving. Okay, it's the place in the code, the continuation that receives the result of the call CC. So what we do is that we call f, okay? We call f with k, meaning that f, if it ever returns, will actually be returning to the continuation of the call CC. And f, as you remember, is a function that receives a function of one argument. Okay? This is a function of one argument that it receives. It receives a function of one argument in the scheme world, in the pure scheme world. But in the CPS converted form, it needs to receive a continuation. Now this continuation is completely ignored. Okay, this is the case where we had cont, in the first example, cont called with 8. This call never returns. Well, why doesn't it return? Because actually the continuation of that call, because there is one, is actually ignored. The function receives the continuation, but actually ignores it and actually uses k to return.
So if it would call dummy k, it would actually multiply by 2, which would give us 6.
Yeah, if you call dummy k instead of k here, basically you would have the identity function. Okay, you would have dummy k result, dummy k result. So it would basically be an identity function. So here we're actually using a closure to refer to the continuation of the call to call CC. So easy to implement once you've done CPS conversion. And in the compiler I wrote, the compiler actually looks at the code to see if call CC is mentioned. If it's mentioned somewhere in the code, then it adds this definition to the program. And if you don't even use call CC, well, it doesn't even bother to add this to the code. Okay, so almost on time here. Amazing. So here's how what the compiler looks like. It's about 800 lines of scheme. It has basically 4 major steps. It parses the source code and expands syntactic forms like let, and so on. Then it does CPS conversion. Then it does closure conversion, and finally C code generation from the result. As I said before, the resulting form is actually very constrained. There are very few features of scheme that are used in the final form. There are no closures, no general closures, because they're now all represented explicitly with calls to a vector or closure in this particular compiler. Call CC is implemented as a library function. There's no need to actually support it especially. If we look at the runtime has basically allocates one heap section. Currently there's no support for garbage collection, but that could be added. I mean, there's no garbage collector. There is actually support for garbage collection in how objects are represented, but no garbage collector. Then there's a table for the global variables. And then there's a small stack for passing parameters, allocating local variables, and also for primitive expression evaluation. This is a really a fixed size stack. It's not a call stack or anything like that. So let's look at it at an example. So when you call the compiler, it actually gives you all of these traces. So you have the source code. So this is the scheme file that was compiled. So we define the square function, takes x, multiplies x by x. And here we have a call to square, and we add 1 to the result. So the first pass parses the text, and here is a pretty print of the abstract syntax tree. So the define has been converted into a set. So here we're setting the square variable to be the function that takes an x and multiplies x by x. So you'll notice that to avoid some name conflicts, the variables are renamed. So this is what's called alpha conversion. And then there's a call to square of 5 and added to 1. Notice also that all the primitives have been given special names just to make them stand out as primitives. That is to say that in this particular compiler, multiply is not really the function multiply, but it's more like a special form. So after CPS conversion, we get this. So what has happened?
You made it even more unreadable?
Huh?
You made it even more unreadable?
No, I just printed this out before I gave this for the talk, so I have to actually parse this first. So what has happened is that, well, this lambda has been converted, so a continuation parameter was added, so it's K6 here. And in the body, K is called with the value of the multiplication. Now this, because we have an assignment of square to a certain value, remember that the rule for CPS converting an assignment requires the creation of a continuation that receives the value that you have here. And this is basically a lambda that's being called, so you get the effect of a let. So we get let R5. R is the continuation that receives the result of this lambda expression. So it's bound to this lambda expression. Then you have the assignment itself, and because the assignment has a result, it's bound to the variable R3. It's actually ignored, it's never used in the code, but it's still there in the CPS form. And then we call square. This is the call to square here. The continuation is the thing that will add 1 to the result. So the continuation receives R4 and will compute in R2 the sum of R4 and 1. This is really the continuation you have here. And because this is the whole program, it has to continue with the call to halt. So now halt is called with the result of adding the square of 5 and 1. So the other argument is 5, so 5 is fast as the value of the lambda. Now, this is before closure conversion, so we still have closures in here, right? We have actually there are no needs for closures. There is a reference to R5 here. Technically speaking, there's no closures in here. But the closure conversion doesn't know that, so it's going to go ahead and actually transform the code. So this is the result we had previously. I just copied it here so we can see the transformation. So for each lambda expression, we actually call the primitive closure. Okay. In this particular case, the closure has no free variables, so it's actually just a vector with one element inside. The function will receive an extra argument, which is the self. Okay, self will receive this closure here, and by accessing the first field of K6, this is a call to the K6 function. We have K6 called here. So we have to call K6, passing K6 as an argument. Okay, and the value that's returned is x squared. And here we have the translation of the call to the creation of the continuation that we have here. So we create a closure. Once again, there are no free variables, so it only has a code pointer, but still it's converted, so self will actually be receiving the pointer to this closure, and that just goes ahead and does the halt. So this part here is when we call square. So to call square, we have to extract the function pointer within that closure, and we pass square as the first parameter, and this basically makes it all work.
Where do we know that K6 is a closure ref?
Excuse me?
Well, the first closure ref.
Yeah. Here?
Yeah. Yeah. Where is K6 not supposed to be a closure?
It is supposed to be a closure. All functions are now closures.
Where is it defined?
Well, K6 will be...
oh, I see. Okay.
Okay, K6 is actually created here. Okay, this closure, when we call square, square is actually refers to this vector here. So when we extract the field 0, we're actually extracting this lambda.
Right.
So we're calling this lambda with square as the first parameter. Okay, that's the self here. Self will refer to this vector that's created here. It's actually unused, that in general can be used to get to the free variables. And then the next argument here is the closure that we've created here. So when we do closure ref K6, we're actually extracting this lambda function pointer. So here we're calling this function. We're passing K6 as an argument, which means that this piece of code is actually receiving the same deal, the closure. And 5 is the last argument passed. So now all function calls of the original program are represented as with this here, where you do closure ref to get the function pointers, and then the second argument is always the closure itself. So this is actually the C code that's generated. So each lambda in the code, coming back to the code here. So each lambda in this code here will actually represent a control point in all of the C program that's generated. What I mean by a control point is a point that can be branched to. Okay? And they will be numbered. I know this one is always called 0. So the whole program, the entry point of the whole program is 0. And then each other lambda will get an integer identifier. So maybe this is 1, maybe this is 2, and so on. So in the code that's generated, there's sort of C code around this that I don't show because it would overflow the slide. But essentially all of this code is embedded within a switch. Okay? The switch that will select the control point to branch to. So when the program starts off, the switch will actually go to the case 0, and this represents the beginning of the program. Okay. Now I've put in comments here the actual beginning of the lambda expression. So that really represents the beginning of the program. This is lambda self 8, this is lambda self 7, and so on. Now these calls here are actually macros. You see macros that are defined at the head of the file. And what begin closure, end closure does is basically allocate a closure on the heap. The arguments that are passed here are the code point, the control point number. So this is the control point 1, meaning this closure contains as a code pointer a pointer to this thing here. Okay. So and 0 is the length. So there are 0 free variables in this closure. So if this were translated into pure C code, it would be something like take the heap pointer, decrement the heap pointer, and store 1 where that heap pointer points. Okay, so it would be basically one instruction, one C instruction that could do this. So it also pushes on this local stack the pointer to this closure. Then it pushes R5. So this is, if we look at the code, we'll see better. Okay, so the very first instruction has created a binding for R5, and that's the first place in the local stack. Okay. And then right here, we have to reference R5 and actually assign it to square. So that's the second line of that code. So the second line is pushing the value of R5, which is at location 0. These are just comments so you can read the code. So you push the value of R5, and then you take the top of stack, and basically you store it in global 0, which corresponds to square. Then you push square, and this is in preparation for a function called square. Okay, it's the function called square of it's the function call that we have here. So we have to prepare on the stack the arguments of the call. So the arguments are a square, and then this closure here. And once we have these arguments on the stack, we can actually go ahead and call square. So that's what we have here. So this pushes the first argument of square. Then we create a closure. This closure also has 0 free variables. And the code pointer is 2, which means the lambda associated with that closure is the one we have here. And then the third argument is the number 5. So we have to push 5 on the stack. And then here we do the jump. Okay, the jump is actually needs to copy values. So we prepared, we had a few values on the stack for these local variables, and then we prepared the actual arguments of the call further down the stack. But the receiver, okay, the function that we're calling, actually expects these arguments to be at the base of the stack. So we need here a copy operation that basically moves these arguments to the base of the stack. So the end jump here actually reads off the code pointer inside the closure that's being called, and then returns to the switch so that the switch will actually branch to the correct location in the code. Okay, so since here we're calling square, we're actually going to end up right here with the arguments that were put on the stack, and etc., etc. Okay, eventually when square calls the continuation, so when it returns the value, it will actually return to this continuation here, this closure, and that adds 1, okay, and then calls false, which stops the computation. it looks very verbose here, but actually when you look at the instructions, if you were to expand the macros, it's actually fairly, it's shorter than what you have here. It's just that this is more abstract and perhaps it's easier to understand. So basically that's it. Conclusion is that CPS conversion and closure conversion are really neat tools if you want to compile scheme to C. They are certainly worth knowing. Even if you don't use them, just understanding them shows you or teaches you new tricks, new programming tricks. So I highly recommend actually looking into those. I actually measured performance, and it's not quite as bad as it first looks like, but the code is about 6 times slower than Gambit C when it's with full optimization. I was actually quite surprised. I thought it would be like 50 times slower or something like this, but it's actually not so bad. And there are no optimizations in this compiler. I mean, there are so many things that could be done to improve performance that maybe the gap can actually be closed to a certain extent. Maybe a factor of 2 slower than Gambit would make sense. And there you have it. In 800 lines of code, something that's actually almost usable. That's it. Any questions?
Well, I was thinking mostly of the first example of the, well, not the first example, but the example you skipped over rapidly for the continuation with the backtracking example.
Mm-hmm.
Would that be available on this website?
Well, these slides will be available, so you can just fetch.
Is the small compiler available also?
Yeah, I'll put that on the webpage.
Well, one question I have. At one point when you were explaining continuations, you said that conceptually they take a copy of the stack, and when you call them, they kind of take this copy and the main stack, they copy back into the main stack and reruns. Is it always the case? Is it really like this that it works, or is it just an image?
No, this is just the concept. It's just to explain the concept. So if you've lived in a world where continuations mean stack, okay, and I think most programmers are brought up that way, that you have a stack and things get pushed, popped, etc., and that's the only model that you have in your mind, then viewing continuation capture as copying the stack is probably the easiest way of viewing this. But I mean, if you look at how it's implemented here, there's no copying. Okay, there's really full sharing of all the continuation frames. So if you capture a continuation here, so you have a sort of a list of frames that are linked, and then later on you capture another continuation within this continuation, then you have 2 continuations that actually share the same tail. So you end up having a kind of a tree-like. So copying is really just a conceptual mechanism to understand how they work. That it would be really bad if it was implemented like that, because if you're very deeply nested in some recursion, you have, I don't know, a few megs of stack, and you start copying things around, and very quickly you'll run out of memory.
Is there a reason for doing the CPS conversion before the closure conversion?
Yes, because the CPS conversion adds new lambdas in your code, and in general these lambdas have free variables. Okay, and since closure conversion is there to eliminate free variables, then you'd just be, if you were doing closure conversion first, you would then have an intermediate form that has no free variables, but then your CPS conversion would add free variables, so you would have to do closure. So you might as well just do it after the CPS conversion. Now, these conversions are, how should I say, they're algorithms, okay, that source-to-source transformations, and they're fairly localized in a certain sense. Okay, I can explain how each of these conversions is done, and I've shown how to put them together in a real system. I believe that whatever you do, if you want to compile scheme to C, I mean real scheme with continuations and so on, and you don't use one of these techniques, okay, you'll essentially be implementing these techniques in various ways, okay, as hacks or as a different expression of these conversions. So the conversions I've shown here are basically just a formalization of what you have to do anyway, okay. And yes, there are optimizations, so you can in certain cases improve on what is shown here, but in essence you can't avoid these things. Okay, these things are going to show up somewhere in your system if you want to have continuations, closures, and so on. If you dream up a better approach than this, I say that there's a way to reduce one to the other. Okay, it's not. They can't really be like a new invention of how to do these things.
But I'm surprised about what you're saying, because if I understand correctly, in Gambit you don't do CPS conversion.
Exactly. But I'm saying that what is done, okay, is equivalent.
Okay.
It's just done in a different way.
Is it? You're pretty sure about that?
Oh, yes.
Yeah.
Yeah.
I'm sure.
Why did you choose not to do it?
Well, it's actually hard to explain. That there are some advantages to actually allocating things on a stack. And for most computation, a stack model works well. Okay? And it's only when you start using first-class continuations, or let's say you have a thread system that actually has to capture continuations and so on, that then you need the power of the techniques that I've shown here. Okay? And what Gambit does is basically postpone these things till runtime. So it uses a stack model, but a stack model that leaves enough flexibility in a certain sense to actually recreate linked frames like I've shown here. So it can be viewed as a kind of an optimization. So it's based on the assumption that in typical code, most of the time a stack model works fine, and it's only when you capture continuation that you actually want to have a special handling. So if this is true, if the kind of programs you compile, this is true, then I think the approach that Gambit uses is best, will give you better performance. Now, if you had a system that captured continuations every function call or every two function calls or something like this, then I'm sure this would win. I mean, this would be superior in terms of performance. Because Gambit is delaying things, but when it actually needs to do something, then it's a little more expensive than what's here. So it's basically a question of trade-off. Okay, my model of computation is that you don't capture continuations very often, but more often than what would what would permit a copying implementation. Okay, some implementations of Scheme think that capturing a continuation with call CC is so seldom that it's okay to copy the stack. Okay, and that's not my model. I really think that captures, if you think of threading and things like this, happen much more often than you think. They're not on every function call, but still it's more than once every few seconds of computation.
What is the current practicality of call with current continuation? Where is it really used except for escapes? Because you use it in the threading system, right?
Yeah.
Okay.
I just gave an example where you can do backtracking in a very, I think, natural way.
Yeah, but that's like a very inefficient way of doing search.
Well, I'm not sure. Why do you say it's inefficient?
Well, it's highly unintelligent.
Well, for this particular problem, yes, it is. But I mean, if you say that backtracking is inefficient, then you mean all Prolog programs are inefficient, or
They have no problems.
that essentially, if you need to do backtracking, then this is a way of doing it. And I don't think that it's particularly inefficient, a particularly inefficient way of doing backtracking. I think it's.
I understood that call CC was expensive.
That's if you implement it the wrong way. Okay. So if you start copying the stack, well, what I mean is really taking a snapshot of all of your stack, then you have real problems.
And otherwise, it's just a question of CPS conversion, or
in one form or another. But definitely, I wouldn't want people to continue the myth. Just like there was a myth that for some is still true, that Lisp is inefficient. Okay? And I think that hasn't been true for the past 20 years. You know, that compilation technology for Lisp, Scheme, and so on has advanced to a point where, Scheme programs can run faster than C++ anytime. Of course, maybe that's not a benchmark, but the same thing for continuations. I think that believing that continuations are inefficient and trying to avoid them because you have this fear that somehow your program is going to bog down if you use continuations is I think, the wrong way of viewing things. I'm not saying that all uses of continuation will lead to efficient programs. Of course, you can shoot yourself with any powerful tool. That if used carefully and the implementation is good, continuations, first-class continuations are fine.
The way I see that is that continuation is a great tool also for language developers. Like in your system, you're using continuations all the place to have a really clean system where you do threading, you do thread. All these are implemented using call CC in a really clean way. For the user, maybe he won't be seeing the call CC as himself using it, but the language, the system you're developing is really robust and clean because they all build on a single foundation, which is call CC.
Call CC is very powerful. I mean, you basically can do all these things and more, backtracking, exceptions, and so on. Now, a novice programmer will have a very hard time using call CC, I think. First of all, the interface to call CC is very awkward. And there's also the power behind it. You know, being able to call continuations multiple times, and so on and so on. I mean, it's non-trivial stuff. So I think it's a great tool for experts. You can create many different types of control structures with continuations. And perhaps the best thing if you have sort of non-expert users is to package these control structures in macros or higher order functions or something like this. Questions? Okay.
So thank you.